What effects has the deconstruction of language had on the theories of mathematics? In order to approach the answer, we need to have a basic understanding of, first, what language is, second, what deconstruction is and does, third, what relation does mathematics have to language, and fourth, how does deconstructive theory apply to mathematics? Let's begin! Language is basically a system or structure through which one can communicate. We use it every day when we interact with one another and even when we think. It is a central part of human culture and identity. Through language, we can carve out and conceptualize the world around us. Some might say that it makes us who we are. Indeed, Martin Heidegger, one of the most influential philosophers of the 20th century, wrote, "We mankind are a conversation. The being of men is founded in language." Because it plays such a large role in our lives, linguists have set out to study language, how and why it works. One of the most famous linguists, Ferdinand de Saussure, worked in developing the theory that language has an underlying structure to it, that it was made up of signs, each of which consisted of a signifier and a signified. However, he stated that the bond between the signifier and the signified is arbitrary, since I mean by sign the whole that results from the associating the signifier with the signified. I can simply say the linguistic sign is arbitrary. Basically what he means is that the assigning of a specific word or symbol to a specific meaning is not determined by any sort of reason or rule, but it is, in fact, arbitrary. There is no intrinsic value in the signifier that connects it with the signified. Thus, the virtue of the sign is in their difference from other signs, not some inherent value that they have. This idea of structuralism was a welcomed new way to look at literature and language. However, not too long after this, Jacques Derrida put forth his theory of deconstruction. He carried Saussure's ideas even further to show that signs were not only arbitrary, but definitions were indeterminable because they didn't point to a meaning, but only to other signs in the system. He said that as soon as there is language, generality has entered the scene. And every sign, linguistic or non-linguistic, spoken or written, in the usual sense of this opposition, as a small or large unity, can be cited, put between quotation marks. Thereby it can break with every given context and engender infinitely new contexts in an absolutely non-saturable fashion. This does not suppose that the mark is valid outside its context, but on the contrary, that there are only contexts without any center of absolute anchoring. This radical philosophy began to erode the belief that there was something in language, some foundational center that gave our words meaning. Regarding this meaning of language, Derrida said, language had become a system in which the central signified, the original or transcendental signified, is never absolutely present outside a system of differences. The absence of a transcendental signified extended the domain and the play of signification indefinitely. This decentering of language brought about the questioning of everything that is built on language, which, according to Heidegger, the being of man is one of those things. If there is no center, or at least not one that we can understand or conceptualize, everything moves into a constant field of play. Since the publishing of Derrida's essay, the principles of deconstruction have been applied to ideas of history, literature, poetry, politics, and even gender. Now, what about mathematics? A few well-known philosophers, mathematicians, and scientists have said that mathematics is the language in which God has written the universe. Logic and mathematics are nothing but specialized linguistic structures, and pure mathematics is, in its way, the poetry of logical ideas. A British mathematician said, "My own attitude, which I share with many of my colleagues, is simply that mathematics is a language, Like English or Latin or Chinese, there are certain concepts for which mathematics is particularly well suited. It would be foolish to attempt to write a love poem in the language of mathematics as to prove the fundamental theorem of algebra using the English language. The language of mathematics consists of an almost infinite amount of signs and symbols and numbers. Now, what relation might this mathematical language have to other human languages? Prominent mathematician Bertrand Russell remarked that mathematics may be defined as the subject in which we never know what we are talking about, nor whether what we are saying is true. Nikola Tesla said that today's scientists have substituted mathematics for experiments, and they wander off through equation after equation and eventually build a structure which has no relation to reality. Uncle Albert tells us, as far as the laws of mathematics refer to reality, they are not certain, and as far as they are certain, they do not refer to reality. What? Did I just hear some of the most brilliant mathematical minds in the history of the world say that mathematics doesn't necessarily correspond to reality or certainty? Let's look at it this way. Pi is the circumference of a perfect circle divided by the diameter. The Pythagorean theorem proves that the squares of the shorter sides of a right triangle equal the square of the hypotenuse. But where in nature could we find a perfect circle or a perfect triangle? Sounds a bit like Derrida's view of language, doesn't it? Now, you may say, but mathematics works. It runs the world. We've been using it for ages. And I agree, it does work. Mostly. But so did language before deconstruction came along. Don't get me wrong though, math does work. It's beautiful and brilliant. It runs on machines and computers, puts things into outer space, and a host of other things. It works within the mathematical system it has been designed for. In his book, What is Mathematics Really?, Reuben Hirsch surmises that, relative to a formal system, one can say that a statement is true if and only if it is derivable in the system. Inconsistent systems can prove all statements and therefore are pretty useless. So when a system is found to be inconsistent, it must be modified. He expounds on the idea of a number. Unfortunately, it's possible to make everything true within a system that isn't necessarily true. It depends on the context it's in as to how you would define it. Is it a real number, a natural one, a rational one? Someone might say, I have a number of friends. To which type of number would they be referring? If math, like language, is a system of infinite signs in constant play, only referring to the signs within the system, perhaps it has some center that, to quote Derrida, is not the center, a center outside itself that gives it validity and truth. Mathematician Joseph J. Rotman criticized such an idea by calling it truth perfect, truth outside time, outside space, outside the material world of matter, energy, and entropy, truth somehow able to be discovered or apprehended, but never invented. Okay, now that you are thoroughly confused, let me wrap this up. What this all boils down to is this. Human language has been shown to be a centerless structure in constant play, full of indeterminacy. If it has a center, an anchor, it would have to be something outside itself, immune to the field of play. Math is a language for communicating quantity and describing the physical world, but it doesn't, at least not exactly. So, as a closed system without meaning, it may be valid, but as a system to describe reality, it doesn't quite make the cut.